that's a recording of John Williams. But how does the sounds we've just heard compare with the sounds that John Williams actually makes on his guitar? Well, every time he plays a note, he creates a pressure wave in the air. And the microphone converts that pressure wave into an electric current. And this electric signal is then converted into another form on magnetic tape. And eventually into a groove on a record. And then there's the replay. The stylus in the groove of the record produces, again, a small electric signal, and that's amplified and fed to the loudspeaker, and the loudspeaker produces pressure waves and the sound we hear. Now, the important thing about all this is that every time the input signal is converted to another form, the output should be a faithful reproduction of it. And if it is, then the sounds that we hear match very closely to the sounds that John Williams originally made. Now, this principle of faithful reproduction runs right through the whole field of measurement and recording, as, for example, in the electrocardiogram. That's a small electric signal which varies with a patient's heartbeat. And the specialist might very well want to monitor this heartbeat, changes in the heartbeat and so on, over a period of time. And what he wants is an accurate and possibly permanent record of this electrical signal. It's this principle of accurate reproduction that we're going to talk about. And to keep things in control, instead of the complicated sounds that the guitar makes, we're going to use a special piece of apparatus which produces very simple and basic waveforms. And we're going to record them on this device, which is called an ultraviolet recorder. And what it does is to produce a trace on a paper tape of an electrical input. Now, the guts of this device is in this little thing here. That's called a galvanometer. And it consists of a small mirror suspended on a very delicate spring. And the whole thing slots into the recorder. The mirror is in a magnetic field, and a beam of ultraviolet light is shone on the mirror and reflected onto the front of the machine. And when an input is applied to the terminals, the mirror rotates and the beam rotates with it. Now, if you have a close look at the front of this machine, you can see a moving light spot. The light spot is the end of the ultraviolet beam. And it's moving because at the moment we're feeding in a periodic signal, fairly low frequency. Now, I can get a recording of this waveform by switching on the machine and letting the paper move. And we'll see what we get. There. Now, because this is a photographic process, it'll take a little while for the trace to appear. It develops in the light, and it's just coming up now. And clearly what we've got here is a triangular wave. Now, the source of the signal is this function generator which I mentioned before. And its output is plotted on the screen of this oscilloscope that you see here. That is the output of the function generator and therefore the input to the ultraviolet recorder. So this is the input, and the output was the trace that you saw on the paper tape. And clearly then the reproduction was pretty good. Well, now I'm going to change the frequency. I'm going to raise it, and you can see the cycles moving closer together as the frequency is increased. Now, on the light spot, as we turn up the frequency, you notice that the light spot begins to move very, very fast, and in the end, you can't actually see the light spot. All that you can see is a rather faint sort of line. So I'm now up to 30 hertz, or 30 cycles a second, and I'll now record that. Before I do that, I'll increase the paper speed to make sure that the cycles are nicely spaced, and we'll record that and see what happens. Once again, we wait for the trace to develop. This takes a little while. And this time, the wave that we get on here is not triangular. The corners are rounded, and the side is distinctly wobbly. So in fact, at this higher frequency then, the reproduction is not as good as it was before. So clearly there's a limit to the frequency at which this recorder can handle triangular waves. But of course we won't always have triangular waves. We might have square waves or a more general sort of wave. So what we really want is a systematic way of describing the performance of this instrument in such a way that it applies to all waveforms.
So Dick has shown us that if we put in a low-frequency triangular wave, the machine produces a pretty good graph. But at higher frequencies, the machine's graph deteriorates. Fourier analysis will provide the mathematical method which will help us to predict what will happen not just for a triangular wave, but for any periodic waveform. If we have a periodic function, we can represent that function by an infinite sum of cosine and sine functions, and that's the Fourier series. We've worked out the Fourier series for a triangular wave in the text. Here are the first three terms in that series. And to get a good idea of how these three terms build up to form a triangular wave, we'll draw a graph of each of these cosine functions and then add them up. We're aiming for a triangular wave. The Fourier series starts with a cosine term. It has the same frequency, but it's far from triangular in shape. The next term in the Fourier series has 3 times the frequency. Adding these two terms gives a graph that looks a bit more like the triangular wave, but it's still a bit wobbly. The third term in the Fourier series is 5 times the basic frequency. Adding this term on gives a graph that's very close to being triangular. The next term in the Fourier series is very small. We need to go in very close to see the effect of adding it on. It straightens the sides a little bit and makes the peak a bit sharper, but it's a very small alteration. In fact, the graph from the first 3 terms is pretty close to being triangular. Adding on later terms makes only small adjustments to it. So we have the Fourier series for the triangular wave. It's an infinite series, but the first 3 terms will give a very good approximation. Now, if we knew how the galvanometer would reproduce cosine functions, then we could predict how it would reproduce a triangular wave by adding them up. For instance, if the galvanometer can't reproduce this term very well, then it won't reproduce the triangular wave very accurately. And that's the key to analysing Dick's galvanometer. Any periodic function can be represented as a sum of sines and cosines. If we know how the machine will reproduce sinusoidal waves, then we can predict how the machine will reproduce any periodic waveform by adding up the response to sines and cosines.
Right, so I'll set this device to give a sinusoidal wave. There it is, fairly low frequency, and I'll record that. And now I'll increase the frequency on here, and I'll make another recording. And here it is. This is the first trace I made at the low frequency, and it looks quite a nice smooth sort of sine wave. And here is the trace at the higher frequency, which also is quite a nice sine wave, but the noticeable thing is that its amplitude is very much less than that at the low frequency. So as we've increased the frequency, the amplitude of the output has reduced. And yet the amplitude of the input has remained constant. If I increase the frequency of the function generator, the amplitude remains the same all the time. So for a constant input, the output decreased as the frequency increased. And I can record that effect by letting the recorder run at a very low paper speed, letting it run, and increasing the frequency of the function generator. and we'll see what we get. It's now recording a very low frequency. I'll turn the frequency up slowly. I'm up to the top of the scale now. That's over 200 cycles per second. What sort of recording will we have on the paper tape? Here we start at low frequencies, and you can see that the frequency increased as we go upwards because the cycles are closer together. Frequency keeps increasing and is at constant amplitude all the time, and continues at constant amplitude until we get to this point there. And just at this critical point, if we increase the frequency a little bit further, the amplitude begins to decrease quite sharply. So at low frequencies, starting at low frequencies, increasing the frequency will at first have no effect on the amplitude at all until a critical point, and after that the amplitude decreases rather sharply. We can plot a graph of the amplitude of the output against frequency. We start at a very low frequency. As the frequency increases, the amplitude stays the same, up to this point, just below 100 cycles a second. Now, as we increase the frequency, the amplitude gets smaller. Now, this feature of the amplitude response remaining pretty well constant up to a certain frequency and then dropping off sharply, that's vital evidence about the performance of this instrument. And manufacturers always give you this kind of information in the literature. They can do it in various ways. Sometimes they give you a graph like this, and sometimes, and especially manufacturers of amplifiers and record players do this, sometimes they tell you that the amplitude response is flat up to such and such a frequency. That means that the amplitude response is more or less constant up to that frequency and then drops off. So this instrument has an amplitude response which is flat up to about 90 cycles a second. Now, John, this curve has been plotted for sinusoidal waves. How does it help us with the problem of looking at other waveforms?
To get an idea how we can use this curve to predict the response of the machine to periodic waveforms, let's go back to our triangular wave. This is the Fourier series for the triangular wave. It's an infinite series, but the first three terms give a very good approximation. So let's see how the machine will respond to each of these terms separately. Cosine is a sinusoidal wave, and Dick told us how the machine would respond to sinusoidal waves. He put in a wave of constant amplitude, and the output was roughly constant up to a frequency of around 100 cycles per second. Then the amplitude decreases. For frequencies greater than 100 cycles a second, the machine's response is not very good. Now remember that in Fourier series we use the angular frequency omega, and that's measured in radians a second. But engineers usually calibrate their machines in cycles a second, but there's a simple relation between them. We have that omega, the angular frequency, is equal to 2 pi times the frequency in cycles per second. In other words, the frequency here, omega, is just 2 pi times the frequency we've measured at the bottom here. So let's put this wave in with a frequency of, say, 20 cycles a second. Well, let's look at each term one by one. The first term, well, that gets reproduced with this amplitude. The second term, that's 3 times the fundamental frequency, so that's 60 cycles a second. That gets reproduced fully as well. And the third term, that's 5 times the fundamental frequency, well, that's 100 cycles a second, and that gets reproduced well also. And so the triangular wave for a frequency of 20 cycles a second gets reproduced correctly by the machine. So let's take a larger frequency, say 50 cycles a second. Well, the first term, that gets reproduced fully. Now the second term, that's 3 times the fundamental frequency, that's 150 cycles a second, and now we've got problems. The amplitude here is less than a half of what it should be. And the third term, well, that's 250 cycles a second, 5 times the fundamental frequency, and that's out here somewhere. That hardly gets reproduced at all. And so the triangular wave, or this frequency, will not be reproduced very well.
And that's just what we saw at the beginning of the program. The first trace, at a lower frequency, was a good reproduction. And the second one, at a higher frequency, wasn't nearly such a good reproduction, just as John predicted. Now, we could have predicted the shape of this output using the amplitude response graph. We feed in the terms of the Fourier series one at a time. The frequency of the first term is 50 cycles per second. It lies in the flat part of the response curve, so it gets reproduced with its full amplitude. The next term has 3 times the frequency. It's beyond the flat region of the response curve, so it gets reproduced with only about half the amplitude it should. So if we look at the sum of the graphs, the graph on the right, the output, is not the same as the input on the left. The third term has 5 times the fundamental frequency. It's way beyond the flat response region. It's hardly reproduced at all. Adding this third term makes the input a good triangular wave, but the output at this frequency is clearly not a good reproduction of it. So, although our recorder reproduces sine waves quite faithfully up to this frequency here, if we feed in a triangular wave, we'll only get good reproduction up to about 1/5 of this value. Now, that's taking amplitude response into account only, but there are other possible sources of inaccuracy in reproduction, and one of them is connected with the time that it takes the instrument to respond to an input. And that time may also vary with frequency, and it's usually referred to as phase shift. Now, we discussed this further in the broadcast notes, and you'll see there that in this particular case, for this particular recorder, if you look after the amplitude response, the phase shift looks after itself. Well, now, I'm going to set this recorder a really severe test. I'm going to feed in a square wave. And that means that the mirror has to stay in one position and move to a totally different position and remain at rest and do the change instantaneously. That's rather a severe thing to ask of a mechanical device. But before I plot any traces, I'm going to ask John to predict the performance of this instrument for a square wave.
To make a prediction for the square wave, we need its Fourier series, and that's worked out in the text. Here, I've started to write down the first few terms in the Fourier series, and of course there are many more of them. How many terms do I need to take this time to get a good approximation? Well, let's have a look at the term involving cosine 19 omega t. The coefficient of that term is minus 1/19. And that is greater than 5% of the first term. And so this term is going to make a considerable contribution to the total. So to build up a square wave, we start with a cosine curve. The next term we add on is 3 times the fundamental frequency. And the next term is 5 times the frequency. So the square wave is beginning to emerge. A couple more terms. And we're now building up to 9 times the frequency. But the curve is still pretty wobbly. The horizontal bits are far from being flat. We would need to add on many more terms before we got a graph that began to look like a good square wave. So for the square wave, the galvanometer needs to reproduce accurately frequencies much greater than the fundamental frequency. So let's see what happens to the square wave for a frequency of 8 cycles per second. Well, the first 3 terms, they're reproduced very well. That's 8 cycles a second, 24 cycles a second, and 40 cycles per second. But what about this term here? It makes an important contribution to the sum. Well, 19 times the fundamental frequency is 152 cycles a second. And you can see that this term is reproduced with less than half the amplitude it should. And so for a square wave with this low frequency, we should be able to reproduce a square wave, but there'll be some wobble and distortion.
Right. Well, I'll set the frequency to 8 cycles a second, which is quite a low frequency, and now I'll record that and see what we get. And it's just as John Berry said. Although it's a recognizable square wave, it's very far from perfect. It's got a lot of wobble on the top, and it's got an overshoot as well. And the same thing goes on the other side. So that's in line with John's prediction. Now, in this program, we've been concerned with the amplitude response of a galvanometer to sinusoidal inputs. And we've used this information in conjunction with Fourier series to predict its response to other waveforms. Now, this kind of amplitude response graph is typical also of a lot of sound reproduction equipment, like record players and amplifiers. And as I've already said, the manufacturers might give you a graph of this kind, or alternatively, they might give you this information in a different form. They might quote 2 figures. For example, they might say that the amplitude response is flat from 30 cycles a second to 15,000 cycles a second. That would mean that this frequency is 30 and this frequency is 15,000. Now, of course, that doesn't mean that any signal will be reproduced up to a frequency of 15,000. If we were to feed in a triangle wave, for example, then we'd get good reproduction only up to about 1/5 of that frequency. And the square wave would be even more restricted. Now, fortunately, most music doesn't contain square waves or triangle waves, but a lot of the notes do have harmonics up to, say, 15,000 cycles a second. And if these harmonics were not to be reproduced faithfully, then the music that we hear would not match the sound that John Williams made in the recording studio.